will not be here today. All right, so we're going to start breaking apart physics piece by piece, making sure you have the proper terminology and vocabulary, because as you start explaining stuff on the free response questions, they want to make sure you use the wrong words. If you accidentally use the wrong word, they're not going to be very gracious to you. So are you too familiar with what frame of reference means?
Yeah.
So what do you all think? What can we put in for frame of reference if we want to explain it in a way that a junior high school student would understand? So think about it this way, like maybe you're standing on the side of a river and then you're watching like a boat go by versus you being on the boat yourself, right? If you're standing on the side of the river and watching the boat go by, the boat looks like it's moving. Whereas if you're standing on the boat, you actually, after the boat accelerates, you don't feel like you're moving anymore. So how could we define frame of reference?
I'd say like your perspective and where you're viewing specific objects, maybe in motion.
The perspective from which, you're right, we should use the perspective, right? The perspective from which a person can determine if an object is moving. It's that same phenomenon, like when you're like sitting in a parked car and then all of a sudden you see a car like backing away. It's actually that car is moving, right? But sometimes your perspective, all of a sudden, it makes it feel like you're moving forward. So always keep in mind when you're frame of reference when you're doing these questions. So that one's a simple one. Now, more important, what's the difference between distance and displacement?
Isn't distance how far something is apart and displacement how far something is moved apart?
You need to be a little bit more specific than that.
Displacement is in reference to where it originally started, while distance is just the amount of distance. I mean,
instead of distance, let's use the word length, right? Finish your sentence, Tiffany.
Oh, sorry, did I cut out?
Yeah.
Oh, so displacement is the length in reference to where you originally started, and distance is the length of movement total, basically.
Total, right? The total length of the path. We'll say, so distance is length that's measured directly from the starting point, right? And then distance would be the total length of the path traveled between two positions, okay? That's gonna be a huge one, because if you accidentally say distance whenever you mean displacement, you're definitely gonna get marked off. So the easiest picture that you can see is like maybe you have a path that goes this way, right? And like squiggly, 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 squiggly. So the distance is me counting all the little like blue parts, right? Versus the displacement would be just a straight line. How far away am I from the starting point? Okay, next part, explaining what a vector is. What the heck is a vector?
A vector is like a movement in a certain direction.
Sure. And then movement in a certain direction. It doesn't have to be movement though, because there's other things in physics that aren't movement vectors. For example, like force or something. Force isn't a movement. So it's like any sort of component that has both a direction and a magnitude. Instead of using the word magnitude, what else could we say instead of the word magnitude?
The amount or the extent.
The amount, yeah. The value, maybe. And let's compare that with a scalar. What is a scalar?
Is it like a multiplier?
It could be a multiplier. That's more of a math term though.
Okay.
A scalar is literally just a number. So scalars, we don't care about if it's positive, negative. We don't care if it's up, down, left, or right. A scalar is just the amount. So like 10 meters per second, 5 seconds, right? We don't care where it's going. So a vector is the amount with a direction, and a scalar is just the amount. Or a lot of times a question will say just the magnitude. So in your experience with physics, what are some concepts that are vectors and what are some concepts that are just scalars?
Like a scalar might be like a weight.
Weight is actually a vector.
Time?
Time is what?
A scalar?
Time is a scalar, right? Because there's no such thing as -3 seconds. We can't go backwards in time. So time would be a scalar. Weight is a vector up here, okay? What are some other concepts that could be a scalar vector?
Like you mentioned before, force is also a vector.
Force is a vector. Well, let me write, it won't let me write off the edge of the page, awful. Okay. Other quantities or concepts that you know of that are either scalars or vectors?
Would constants also be a scalar?
Constants? Like what kind of constants?
Well, I was kind of thinking about gravity, but then you can also, I guess, have, well, could be negative too, I guess.
Yeah, it's gravity. Tell me, is gravity a scalar or a vector?
It's a vector.
Gravity is a vector, right? So what about speed? Is speed a scalar or a vector?
Scalar.
Scalar, speed is a scalar, right? We don't care about which direction it's going. Do you have the worksheets, Bobby? Okay. What's the symbol we use for displacement? Usually in physics.
I didn't hear the question, but
Oh,
I think
I moved on to the next one. What's the letter that we use?
X.
X, right?
Yeah.
So we use the letter
Or
X.
Y direction, I did the Y.
Yeah, but I think a lot of times in the questions they'll just say X too. And it's up to you to use Y. So X is a general letter, so we'll change it to Y for vertical. And this one's easy, right? We measure the SI unit is going to be meters, not hard. Okay. So now everybody knows what velocity is, but how would you explain it in a physics way? So we want to give a word for average speed, and we want to give a word phrase for average velocity. What is average speed?
The average distance traveled in a set amount of time.
Average distance traveled in a set amount of time per a fixed amount of time, or per an elapsed time. Yes. Instead of average distance traveled, we could also use the average rate of change as well. Right? Good. So that's average speed. What about average velocity? Oh, wait, I just realized, Tiffany, you shouldn't have used average to be total distance. Total distance traveled per an elapsed time. Instead of using distance for velocity, we should use the word displacement traveled in an elapsed amount of time. We can't use the phrase average rate of change there though. So average rate of change is synonymous with speed. Do not use average rate of change for velocity. It'll be the displacement over that fixed amount of time, over that elapsed amount of time. So if we think about it earlier, we said speed was a scalar, right? So speed is a scalar. And guess what? Distance is also a scalar, right? So these two go together. These are just numbers. I traveled 10 miles. I traveled 50 feet. Versus velocity. Velocity is a vector. That should make sense, right? They both start with V's. And then what do we have? We have displacement. Displacement is also a vector. So if you understand which family of numbers they belong to, then you can also figure out their how they relate to each other. So what does velocity have that speed does not have?
Direction.
Direction, there you go. And then the symbol for time, that one's easy, right? Time is t, measured in seconds, right? O is in seconds. And then the symbol for velocity, regular v. And then this one's easy, right? Meters per second. And then how is average indicated on the symbol for velocity? What are we gonna do to this v? We're going to put, oh my gosh, I'm trying to do zoom and this thing. We're gonna put in a little bar above the v. So that'd be for v average. So for the purposes of physics 1, you can say that the average velocity is just gonna be the initial velocity plus the final velocity, and you just literally divide it by 2. That's not gonna work for physics C. You're gonna have to do some extra calculations. So that's the average. And then what symbol represents the word change? The Greek letter D. We're gonna use the word delta. Right, so that's gonna represent the change. That's a capital D in Greek. And then what mathematical operation do we use when we're finding change?
Is it the subtraction sign?
Subtraction sign for difference. Yes, we subtract to find the change. So the final minus the original. Also, please keep track that you're putting the result first and the beginning second. Okay, so then we're going to try this out then. So we have this trip by Fred and we have this trip by Frank. So we want to find the displacement, the average speed, and average velocity for Fred. So, oh, and distance. Sorry, I skipped distance. Let's do distance first. What is the distance that Fred traveled? And let's assume that each block is 1 meter, right? Each square is 1 meter wide.
He traveled 15 meters.
15 meters. Perfect. What about the displacement?
3 meters.
Is everybody satisfied with Tiffany's responses? 15 meters and 3 meters? Something is wrong. Not the numbers, but something else is wrong. What is wrong?
Oh, direction.
Direction. Which one needs a direction? The top or the bottom?
Bottom.
Bottom, right? We need to say direction. If we don't, they're going to mark you off maybe a half of the credit or a full point. Sometimes they won't give you a credit if you do not give a direction. So be careful there. What about average speed, please?
1.5 meters per second.
1.5 meters per second. Average velocity then?
0.3 meters.
0.3 meters per second.
East.
One of these, east, right? One of these needs the direction. It's that bottom one. Okay. So then similarly over here, right? So then we just count up the squares, 3, 6, 3. So that's 12 meters. Displacement, we just count the final minus original. So Frank moves 6 meters to the east. Average speed would be distance over time. So 12 over 12, which is just 1. And then displacement over time. So that's 6 over 12, which is 0.5 meters per second to the east. Okay, not bad. Now it says the first thing Fred did was go south for 4 seconds. If he wanted to cut his average speed in half, how long should that southward motion last, assuming the other two motions are exactly the same? And to help, I'm going to rewrite the average speed at the beginning, right? Beginning was originally 15 over 10, right? Before we simplified. We want to cut his speed in half.
Seconds.
We need a total of 20 seconds, right? Because what basically to cut the speed in half, we want to double the time, right? But they're saying we just want to change this component of his traveling. So somehow we want it to total 20 seconds. How would we change the southward motion?
14 seconds.
Make it 14 seconds, right? Wait an extra 10 seconds or extend by an extra 10 seconds. So then would this amount of wait time have also halved his average velocity? So let's go back to this one then, right? What was this originally? This was 3 meters per 10 seconds.
The new average velocity would be 0.15.
So it would have also halved his average velocity, right? So this one would have been yes. Yeah? Any questions on that one? Okay. So we've been calculating average speed and average velocity, right? Now, what about instantaneous velocity? How's that different?
It's the velocity at a specific time given.
Velocity as measured at a specific or a precise moment of time. Yeah, whereas, what is average velocity then? The change over a long, we can say long in quotations, right? Over two points in time, right? We have to calculate 2 points in time to figure out the average velocity. So within a speedometer, what does the speedometer in your car measure when you're driving down the street and you see, oh, 50 miles per hour, 60 miles per hour? Is it measuring the average speed, average velocity, instantaneous speed, or instantaneous velocity?
Instantaneous speed.
Instantaneous speed, right? And why is it instantaneous? And why is it speed and not velocity?
Because it measures like how fast you're going like at the specific time and not necessarily your direction.
Doesn't measure direction, yeah. So we'd say doesn't measure direction. And the other part is, right, when you go backwards in your car, the speedometer is still going to go up. I don't know if you've ever seen somebody do that, but yeah, if it went backwards in a real life, it technically should go down below 0, right? So we'll say doesn't measure direction. Good. So that's a pretty easy one. So then on the AP Physics test, they love asking you procedural questions like this then. So let's suppose you do want to measure the car's average speed. We want 2 instruments that you can use in a car, and explain how do you use these instruments to calculate average speed. Any thoughts on this one?
Maybe like a stopwatch and a GPS.
Stopwatch and GPS. I like stopwatch and GPS. What could we use instead of a GPS though?
A speedometer.
Speedometer. I'm not going to use a speedometer because the speedometer measures instantaneous speed. And the worst thing you can do with the speedometer is then you're like, oh, right now I'm going 20 miles per hour, then I'm going 21, then I'm going 22. You'd go crazy trying to capture all the different speeds along the way. So we do not want to use a speedometer when you're calculating average speed. So if you ever get one of these questions that's procedural, let's go back to think what equations we can use, right? So the equations for average speed was what? We wanted average speed. And then to do that, we could use total distance, right? That's what we want, total distance over total time. So the stopwatch is good to help us measure the time. The GPS could help us find distance. What other things can allow us to calculate distance? If you want to be crazy, you could grab a ruler and chase after the car with a ruler.
Maybe like a map if you
Interesting map.
already
Okay.
know where you're going.
Yeah, maybe, but this is probably not going to work in a lab setting, right? So we're not. I appreciate the thought. We want something a little bit more accurate than what else measures distance? You could pre-measure out a thing. Do you know the thing in the car on the bottom underneath the speedometer? The little thing that turns, it's like 1, 2, 3, 4, 5. The odometer. Right, a distance tracker too. Like now we have these things on our watches, like they have a pedometer too. So like if you're tracking people like running a race or something, you know, you could do a distance tracker on them. So anything that tracks distance. I know I'm being nitpicky, but GPS totally would work. When you're measuring smaller things, you're going to do like a ruler or measuring tape or something like that. Yeah. Okay. So that's the idea of measuring average speed. Now, what the heck is acceleration described in words?
It's the velocity over time.
The change in velocity over a elapsed period of time. The amount that velocity changes per unit time, right? So we want to think about the idea of change. Same with speed earlier, right? The total distance, or I guess the change in displacement over time works for velocity too, right? Here, the acceleration, A, easy, right? And then units, meters per second squared. I'm sure you're familiar with it. So where the heck does this square come from? if we're doing velocity over time, right? Change in velocity, well, if we literally take the unit and divide it, right? So it's just like a dimensional analysis thing, dividing a unit is the same as multiplying by the reciprocal. All right, we can multiply units, and we should multiply units when we're doing physics. So then let's fill out this Mad Libs about acceleration. If the car's acceleration is +5 meters per second squared, that means the car's blank increases by 5 blank. What's the first blank?
Speed.
Velocity.
Velocity. We need to say velocity. We cannot say speed. The car's velocity increases by 5. What units?
Meters per second.
Meters per second for every blank of blank. For every, we want unit here. Every second of what?
Time.
Every second of time. I know it's being like very, very like annoyingly specific, but they want you to be that specific when you're answering your pre-response questions sometimes. Right? Acceleration is a vector, as a reminder. So it's change in velocity, not change in speed. A car is advertised to go from 0 to 60 in 2 seconds. When this happens, the car is blank. Ooh, this one's interesting. Now we're talking about a car. So the car is blank. What about the car that changes?
Is it its velocity?
For this one's gonna be speed, right? Because we're talking about a car, and we just talked a second ago about the car's like speedometer, right? It doesn't measure velocity, it's just like how fast it's going. It doesn't care about direction. So this one, when we're talking about real life scenario, we're talking about the car's speed. The car's speed, what does the car's speed do?
Increases.
Increases by this one. Ooh, what the heck happens here? 60 miles per hour in 2 seconds. So the car's speed increases by how much?
It'll be 30 miles per hour every second.
30 mph every second of time. So in this case, the car's acceleration measured here would be positive. Oh, how would you write this? It would be 30 miles per hour seconds. I don't think they'd have a question like that on the test, but it's per second, right? So we want to make sure we divide by the number of seconds. And then object is falling. We're going to use 10 on the test, right? You're not going to use 9.8 or 9.81. So the blank of the blank, blank, blank. The pennies. Physical quantity. The pennies velocity. Does it increase or decrease?
Increase.
I guess it depends on how you're measuring it, right? Typically when we do down, it's going to be negative. So I guess it depends on if you're measuring plus or minus, right? So if we go with the minus, the velocity technically decreases because it's falling down, right? I guess both could be true though. So you just want to make sure you set up your direction correctly first. So the penny's velocity decreases by 10 meters per second of velocity per second. That one's being pedantic again. Okay, and then velocity is rate of change of what?
Of displacement.
Of displacement. And then acceleration, just to reiterate, right, is we're not going to use distance, we're going to use displacement. And then acceleration is rate of change of velocity. So please keep that in mind as you're doing your assessments. Okay, so we have all these famous equations that you're all familiar with by now, right? And then most of these will be given. Do I mean most? I actually should have an AP Physics sheet out right now because I don't remember which ones are given and which ones are not. So let me look that up really quickly, just so we'll highlight the one that you actually need to know. Let's see. AP Physics 1 equation sheet. Which one do you need to know? So they give you this one for sure. Which else? They give you this one for sure. Which one? They give you this one. I think the one they don't give you is this one they don't give you. But that one's pretty easy, right? This one's literally the distance equals rate times time formula. And then y'all should be familiar with what these things mean, right? So I guess if they don't put a subscript next to it, that's going to be the final, right? And anything with the little 0 next to it, not, is going to be the initial. So I think this should all make sense. So I'm not going to spend too much time there. Now I do want to do the multiple representations of acceleration exercise because this can be tricky for a lot of people. So this one, they give you the position function, right? So we can go ahead and plug in various times for the position function. You don't need a calculator to do that because I think I already did it out earlier. What is it? 50, 32, 18, 8, 2, and 0, right? So I'm plugging in the numbers for distance or position, right? So now how the heck are we supposed to calculate velocity based off of those numbers? I'll plot in the points while you think. So in this case, the distance and displacement are going to be the same because the object's not moving up and down and all over the place. So remember that we can calculate the average velocity in AP Physics 1, right? The average velocity is just the change in distance or change in displacement over time, right? So how much was this object displaced? Well, this object was displaced 18 in the first second, right? And it's per unit time, so we can say this is just 18 over 1. So that's just 18. And then same thing over here, right? How much was it displaced in that amount of time? This one was displaced, what is 32 to 18? That's 14. And how much was it displaced here? It was displaced 10. So I'm purposely trying to write it in between on the line. Okay, so I'm purposely trying to write it on the line. Why? Because we're calculating an average rate of change. In AP Physics 1, you're not expected to calculate the instantaneous rate of change. If you know calculus, you can calculate the instantaneous rate of change, the instantaneous velocity, by taking the derivative. So if we were to take the derivative of this, this becomes 4t, and then this becomes minus 20. So for those of you who are interested in taking the derivative, this 2 goes down in front, and we just times it by 2, and then we just minus 1 from the power. So that's how it becomes 4. Same thing with this t. This t has a 1 exponent, so we bring it down in front and we just, that t goes away. If that's too confusing, we're not going to worry about it. But we can go ahead and calculate the acceleration while, so see if you can calculate the acceleration while I plot the points. I'm going to plot it in between here. 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 Anybody get an acceleration? So remember that acceleration is the change in velocity over a unit of time, right? So these are still a second apart. So what's the change here? It dropped 4, right? Oh, I should have put, shoot. I forgot to put the negative sign. It dropped, so these should all be negative numbers. -18, -14, -9, -6, -2. So I drew that one wrong. So if it's going from -18 to -4, it's actually increasing by 4 units in that 1 second, right? It went from -14 to -10, so it's increasing by 4 units again. Increasing by 4, increasing by 4. Yeah, so if I wanted to plot the points, they should actually be here, here, -10 here, -6 here, -2. And then we connect the dots there. And the acceleration is constant here at 4. So then if we want to write the acceleration formula, it'd just be a is equal to 4. And for AP Physics 1, you can assume that acceleration is going to be constant, unless somehow they state otherwise. We're going to assume acceleration is constant. Any questions on how I got all these points? Okay, so here velocity, I almost got tricked, right? So here velocity is negative and acceleration is positive. Okay. So let's do this exercise again. We're going to do 6 different ones. So now that we get the hang of it, we can go through some of these pretty quickly. Then here, what is 0? So 0 is 0. 125 minus 5. 105. Plug in 9. 45 is 80. Plug in 4. 16 times 5 is 80. So that's 45. And then plug in 5. 5 times 5 is 125. That's 0. What I put there? Okay, so then what's the velocity for the first one?
Positive 120.
120, no. Remember, the velocity is the change in displacement. That change.
It's 5.
And don't be tricked like me. It's -5 because it's going down. Yeah, what's the negative one? Next one, sorry. What's the next one?
-15.
Yep, -15. And then -25. And then, oh, I might have done this wrong then. Is it? No, I did it right. 35, and then it's -45. And look, what's happening here? The acceleration is going up or down? It's going down, right? 10, 10, 10, 10, 10. Okay, so in this case, if I want to write the formula here, how much is the velocity? The velocity is going down by 10 units. And then it's technically, if we take the derivative of this, you don't need to know this, but if we take the derivative of this, it'd be 0. And then the acceleration is -10. Okay, so the velocity is changing by 10 units per second going down. So velocity would be something like this. And then if we plotted all the points here, it looks something like this. And then if we plotted this graph, it looks something like this. Okay, and I want to make sure that this one's linear, so I'm going to make this a straight line. There. Cool. This one's easy. It's 0, 10, 40, 90, 160, 250. We're going to calculate the change, right? So it's 10, 30, 50, 70, 90. So then what'd the acceleration be here? 20 units per second. Ta-da! And then this one's going to be a straight line starting from here, going up to 90, something like that. And then this one be 20. So in this one above, what do we have? We have velocity is negative and acceleration is negative. Here we have velocity is positive, acceleration is positive. We're looking for where it is on the x-axis, right? If it's above the x-axis, it's positive. This one, what is the the change of distance? It's changing by 20 units per second. It's starting at 0, and the acceleration is a constant 20. Okay, let's go through these really quickly. So then this one would be 0. This one would be 9. What happens when we plug in 2? 2 is 20 minus 4 is 16. Oops. Whoa, why are you doing this? So what was this? 9, 16, 90 minus 9 is 81. 160 minus 16 is 144. And then 50, wait, I'm doing this wrong. 30 minus 9 is 21. 40 minus 16 is 24. 50 minus 25 is 25. Great. So what is it changing? 9, 7, 5, 3, 1. And then minus 2, minus 2, minus 2, minus 2. So it's changing by 2 every time, starting at 10. And the acceleration is negative 2. So we draw this straight line here. We draw the straight line here. And then we draw something that looks like a parabola there. So in this case, velocity is positive and acceleration is negative. These are easy, right? So these are straight lines. So it's 50, 40, 30, 12, sorry, 20, 0. This one's easy, it's just dropping by 10 every time. And in this case, what's happening to the acceleration? It's not changing. So we'd have a straight line there, we'd have a straight line there, and then we'd have a straight line here. So in this case, the velocity is negative, the acceleration is 0. If we want to do the equation here, it'd just be negative, though there's no t, right? The acceleration is just, velocity is just negative 10, and the acceleration is 0. And finally, the last one, if we plug in, it'd be 0. Sorry, if we start at the beginning, it'd be 10, 15, 20, 25, 30, 35. The velocity is upping itself by 5 every time. And then the acceleration is none, 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 none. Draw a straight line there, draw a straight line there, draw a straight line there. Since the velocity has no variation, it's just going to be v is equal to 5, and acceleration is 0. Okay. So I hope you were able to keep up and draw all the patterns here, because we're going to need to start analyzing these patterns. So does anybody need me to scroll back to see some of the first 3? There's literally going to be these 6 patterns when you're analyzing graphs. So let's discuss all these patterns then. look at the 6 situations you just considered and complete the following general rule. When the velocity graph is positive and the position graph is positive, what's happening? So which one is that one? Where it's going to be example number 3. What happens when the position and the velocity graphs are both positive?
Acceleration is positive too.
Acceleration is positive too. Sorry, I misread the question. It says when the velocity is positive. So when the velocity is positive, what's happening to the position graph? When the velocity is positive, what's happening to the position graph?
The position graph, I guess, like increases.
Is increasing, right? Is increasing. Yeah. So we're going to put that there, right? When the position graph is increasing. So then what does that mean? Well, if it's negative, I think it should make sense what the opposite is, right? When it's negative here, right? When it's negative here, when it's negative here, they're always decreasing. So that should be pretty straightforward when the position graph is, will it let me write? Maybe I'll have to use my pen. Decreasing. Okay, now the next one, when the acceleration is positive, what's happening to the position graph? Acceleration is positive. So that'd be graphs 1 and 3. Ooh, what happens when the acceleration is positive? What thing does graph 1 for the position and graph 3 for the position share in common? So there's this concept called concavity, right? These graphs are both called concave up. They're sloped in such a way that they would make a cup shape. Does that make sense? This is concave up and this is concave up. So when the acceleration is positive, your curve is either going to be shaped this way or shaped this way. So we'll say the graphs are concave up. So we can say the same thing backwards then, right? We can say concave down if the acceleration is negative, right? So if something is concave down, it's going to make like a shape like this, right? An upside down U. Concave up, it would be like part of an upward U, right? Concave down, it'd make like an N shape. So let's look at, it'd be which one? It'd be graph number 2, right? Graph number 2 is concave down. It's part of this N shape. And then I need to look at graph number 4. I must have plugged in something wrong. If it's, because it should be concave down here too. Did I plug in numbers wrong? 0, 9, yeah, it should be a concave down graph. So let me fix the first graph. It should look more like 0, 9, 16, 21, 24, 25. So it should make a concave down shape. There, so it's like part of an upside down N shape, right? It's half of the N. So anytime you have a negative acceleration, it's going to make either this part of the N or this part of the N. Okay, and the last one is saying if the acceleration is 0, what can you tell me about the position graph? Well, if the position is, or acceleration is 0, then the acceleration graph is going to be linear. It's not going to be curved anymore. We can't determine which way the slope is going though. So notice in both cases, we know that the acceleration is 0 and we see that the position graph is linear. Now, what about this? When the acceleration is positive, what can you tell me about the velocity graph? Let's see. Positive in 1 and 3. What is the same about the velocity graphs here?
It increases.
Increases at a constant rate. When I say constant rate, that means it's increasing in a line, right? So we're going to say here, if it lets me. Oh my God. Good job, Notability. Not letting me write. Increases at a constant rate. or instead of saying rate, we can say constant slope too, right? So rate or slope. So then what would that tell us about negative? It would be decreases at constant rate / slope.
Did you say linearly?
Oh yeah,
okay.
increases linearly, decreases linearly. We'll write that there too. I like that. That's so much more concise. Decreases linearly. And then what do you notice about when acceleration is 0? Well, in graphs 4 and 6, or 5 and 6, right? When the acceleration is 0, then the velocity is also constant, right? Constant. Constant here means not changing, horizontal. / horizontal. So please pay attention, right? Constant by itself means this. Constant rate means this or this, right? Constant rate. Now, this is the hardest part about understanding these graphs. When the object is speeding up, acceleration and velocity have the same sign. When an object is slowing down, acceleration and velocity have opposite signs. So let's look at the graphs that have the same sign then. So graph number 3, right? Graph number 3, velocity and acceleration is positive. That means the position of the function, you can see it's speeding up. The position graph is getting quicker and quicker and quicker. It's sloping upwards faster. Now let's look at graph number 2. The velocity and acceleration are negative, and look at the track, right? It's starting off slow, but then it's dipping faster and faster and faster. So it's speeding up in the negative direction. Right, so speeding up can have this downward shape. And so these both are beneath the x-axis. That means the object is speeding up. Now let's look at graph number 1, right? Graph number 1 shows us that velocity and acceleration have opposite signs. So you can see it starts off steep, but then it kind of narrows out a little bit, right? So this is a graph of an object that's slowing down. Same with graph number 4, right? It's starting by increasing quicker, but then it starts to narrow off and taper off and taper off. So this is also a graph of an object that's slowing down. And then you can see the velocity and acceleration have opposite signs. Does this concept make sense? I think this is the most confusing part about this chapter. Bueno?
Yeah.
Okay. So then these should be pretty straightforward, right? They give you the equations and they're like, okay, figure out how to do this. So I want you to like just stick with this method, right? When you're doing a free response question, write down what you're given, write down your unknown that you're looking for, figure out the equation on the sheet. Hopefully there's one on the sheet that you have to help you, and then solve and substitute. So in this case, what are we given for number 1?
Distance and time.
Distance and time. So x is distance. So we'll say x is 100, and then we're saying t is 8. And then what are we looking for?
Average speed.
So we'll use s for speed, right? Or you'll see in some things you could also write speed as the absolute value of velocity. Right, so we can use either of those symbols. Equals question mark. Okay, which equation allows us to do that? We can use this one. I think this one's also easier to write this way, right? V. So then, what is that? 100 is equal to absolute value of V times T times 8, right? And then 100 over 8 equals absolute value of V. And then this speed is equal to 12.5, right? These shouldn't be too hard. So not going to worry about too much of these questions. Okay. We'll move on to free fall. What kind of motion is free fall?
Is it just
Velocity,
like
right?
vertical motion?
One at a time, Bronson, then Bobby.
Constant velocity.
No. Bobby.
Oh, I just said vertical motion.
It's one of these four: constant position, constant velocity, constant acceleration, changing acceleration. Said no to constant velocity.
Constant acceleration.
Constant acceleration. Because think about free falls when you drop an object, right? So when you drop an object, it starts off barely moving, right? The exact second I drop it, it's going to start off slow, and then it's going to speed up, speed up, speed up, speed up, speed up, until it reaches something called terminal velocity. Terminal velocity is when an object can't speed up anymore. And on Earth, that happens because air resistance prevents it from speeding up. What is that constant acceleration? Well, that constant acceleration is equal to negative 9.81 meters per second squared, AKA gravity. Right, so anytime you see a question that says free fall, we're just gonna assume there's gravity of whatever planet we're on. I guess later on, we're gonna be on different planets. Are you all familiar with this like half infinity symbol?
I've never seen that.
This is a phrase that you can use when you're answering questions. Here we can say that distance is directly proportional. So that symbol means directly proportional. You're going to use that a lot in your physics test. To time squared. Whenever you see something that is directly proportional to something, that means we can write it as an equation that d is equal to some number here, this k is some number, times t squared. This is the equation that we're going to be using, and this should look really familiar, right? So here, what's the equation we can use? We can use this equation for free fall. When something is in free fall, we start off with no velocity. So the equation we can actually use if we want to do the free fall equation is d is equal to 1/2 gt squared. So the constant of proportionality is just 1/2 g. That's your constant of proportionality. It's going to go on the side of the page. Proportionality. Why is it such a long word? Any questions on that? So this is our equation for finding d when you just drop an object. Okay, so there's no figure for me to show, but you know, there's this whole idea, they talk about how Galileo would like throw watermelons and like, I don't know, like raspberries off the side of the Leaning Tower of Pisa, and they'd hit the ground at the same time. So can you all explain, why does that not happen when I drop a piece of paper or something? Drop a piece of paper in a watermelon. Why does the paper take longer to fall?
Probably because of like,
Bobby?
oh, sorry. I just said like air resistance. Maybe.
Tiffany, what were you saying?
The mass is different.
Let's assume that they have the same mass. Okay, so then I have a ball and a piece of paper that weigh the same thing.
Did you say surface area?
You could say the surface area, yes. I actually think the surface area would capture more air, right? The surface area would be exposed to more air. So theoretically, if I could drop a piece of paper so that it's perfectly like this the whole time, technically it would fall the same rate as something more solid. Right, so we could say surface area too. So then how the heck are we going to get it so that they fall the same time then? We'd want to get it into a vacuum, if you were, they've done this experiment where they put a bunch of feathers in a vacuum, because feathers are just like floating everywhere, right? Then they've done it where they suck out all the air, and literally you drop the feather and the feather goes thwomp, right? They just fall because there's no air like pushing them up. Okay, so then we have this free fall idea then. So a person throws a ball upward near the edge of a building as shown. Ignore air resistance and use gravity as 10 meters per second. The first white dot is the position of the ball when it leaves the thrower's hands. Each white dot after that represents the ball's position every second after the ball leaves the thrower's hands. So in the table below, the time represents how many seconds after the ball leaves the thrower's hands. Fill in the speed, velocity, and acceleration after each second. So out of all of these, which one do you think would be the easiest to figure out first?
Probably the last one.
We're gonna assume the last one's the moment before it hits the ground, so we're not gonna assume that it's 0. I know that's why you said the last one.
In the beginning.
We don't know the beginning, it just said it left his hand, so it's like impossible right now to find out.
The ball at the highest point.
The ball at the highest point, that's the one we can figure out, because why?
Because gravity is the only acting force.
Gravity is the only acting force. Huh. Gravity has only been the acting force. Once the ball leaves its hand, there are no other forces on the ball. So your statement doesn't work, but I appreciate that statement because gravity is the only acting force the entire time.
Would it be that the velocity is equal to 0?
We're gonna clarify and say the vertical velocity is equal to 0, right? So the vertical, we're assuming this ball is going vertical, even though there's a little bit of an arc here, the vertical velocity is equal to 0, AKA the speed is equal to 0. So Tiffany said, gravity is the only acting force, and I expanded upon it saying gravity is the only acting force the entire time. So what can I say? I can say that it's -10 here, 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 here. And in AP Physics 1, we're going to assume that gravity is constant or acceleration is uniform. Sorry, acceleration is uniform. And what do we know about acceleration? Acceleration is the change in velocity. So we can start stacking the numbers here. It's saying every second the velocity is going to change by 10. It's going to dip by 10. So once we know that number, we can start filling this whole thing in, right? So this will be 10, this will be 20, this will be 30. And if we want to go backwards, we're going to add 10, right? And then how does that relate to speed? Well, speed is just the absolute value of velocity, right? So this is 20, 10, 10, 20, 30. So there's some interesting parts here, right? We see that this, and then we see that this, right? Is it a coincidence that these two spots have the same quote unquote speed? They have the velocity and the speed are the same number? What about over here? Is it a coincidence that these two have the same number also? It is not a coincidence. So one thing I do want you to think of is that if they have the same height, assuming there is no air resistance, right? No other things playing into the factoring into this, at every point, the object will always have the same speed, not velocity, right? They will have the same speed. So that's another trick when you're doing some of these kinematic equations. Well, I start here, the ball's gonna go up at 10 miles per hour. So over here, it's gonna go down at 10 miles per hour. Same speed, different direction. Make sense there? So when the ball is at its peak, right? We know for sure we're going to clarify to say it's vertical velocity, because there could be a horizontal component, okay? Its vertical velocity is 0. Each second, the ball's velocity, we're going to say decreases by 10 meters per second, or we can say 9.8, right? Whatever we want, but technically it's 10 for the test. It's the easy number they want us to use. The speed is almost the same as the velocity except for its sign. Right, and how does the ball's acceleration vary with time? In physics 1, it's UAM, uniform accelerated motion, so it doesn't. Yes? Okay, so then we're gonna analyze all these motions then. So if we want to analyze all these motions, how can a curve be considered to have a slope? So if we have a curve like this, right, we want to find its slope, how do we do that?
Find 2 points.
We can do that. We can find 2 points, right? You can find 2 points and draw a line through them like that. The better way is to draw a single point and try to draw a tangent line, to try to like draw a line perfectly perpendicular to find a point and draw a tangent line. Or you can pick 2 points that are really, really, really close together too. How can the velocity of a certain time be found at looking at a position versus time graph?
It would be the slope.
Find the slope of the tangent line at that point. At that point, good. And then how can the change in position between 2 times be found from the velocity versus time graph? The change in position / displacement, right? Position is the same as displacement here. Find the area under the curve. So to find the position or displacement, we want to find the area under the curve of the velocity graph. How could you find the acceleration by looking at the velocity versus time graph?
It would also be the slope.
The slope of the tangent line again, right? Slope of the tangent line. And then same thing for the last one, right? How do you find the change in velocity? It's to find the area under the curve. Okay. So let's test our understanding then. So we have these 6 graphs, right? And we want to match all of these. So which one shows the object moving forward with constant velocity? So we want to pick 1 through 6 for the first one, and we want to pick A through F for the second one.
Is it just graph 3 and then graph E?
Graph 3 and then graph E. Good. Everybody agree? And what is the acceleration here then?
0.
0, right? I need to grab the door really quickly, so I'm going to have you do the remaining 5, and I will be right back. I am back. Did y'all get anywhere on these?
Will the next one be graph 5 and graph B?
The object is moving backwards with constant velocity, graph 5 and graph B, correct. 0 acceleration. What about the next one? Forward and speeding up.
1F.
1F, excellent. What is the acceleration here then?
Positive.
Good. Next one?
2A.
2A, excellent. What's the acceleration here?
Oh, negative.
Negative, right? Acceleration, velocity, or positive, or same sign. Moving forward, slowing down.
4 and C.
4 and C. And then what's the acceleration here?
Would it still be negative?
It has to be negative, right? Because C is like, it's positive here, right? We talked about how for things to be slowing down, they have to have opposite signs. And last one?
6D.
6 and D. Good. And then what would the acceleration be here?
Positive.
Positive, right? Because then the velocity is negative and the acceleration is positive. They have opposite signs slowing down. Okay, so being able to dissect these graphs is pretty helpful here. This is a position versus time graph. When is the object moving the fastest? The position versus time graph. So we'll answer 0, 1, 2, 3, or 4.
At position 1, or I mean 1.
Actually, I think the answers here, I've kind of misled you. I think the answer needs to be a decimal. Because fastest means like speed or velocity, right? And we said a second ago that if we're trying to find velocity, we need the slope of the position graph, the slope of the tangent line. So at 1, look here, the slope is like this, right?
It's flat. I'm drawing a tangent line there. This is flat. If I want the fastest going forward, that means I want this highest sloped up. So where is it sloped up the most? Probably here around 0.5, probably here around 3.5. So we'll say 0.5 or 3.5, right? Because that's where it's sloped up the most. So then if it says when does the object go backwards the fastest, then that's where is it sloped down the most? Where is it sloped down the most?
At 1.5 or 2.5?
I think actually right here, right in the middle at 2, right? So somewhere in this range, right, at 2. At what point does the object have 0 velocity?
One and 3.
1 and 3, right? That's where the tangent line is flat. It has no slope. During what interval does the object have positive acceleration? Uh-oh, we talked about positive acceleration when we have this concave up shape. When is my graph upwards concave?
2 to 4.
2 to 4, right? 2, 4. And then negative acceleration is concave down shape, right? So that'd be 1 to 2, or 0 to 2, excuse me. Right, so the concavity of the graph. Okay, now this one's a velocity graph, so that's confusing now. So now we have the speed, right? We have the speed in front of us. At what time does the object go fastest forward?
It'll be 3.
This one's not 3. So this one's literally the velocity in front of us. So when is velocity the biggest?
At 0.
At 0, right? That's different from the position graph. At the position graph, we had to look at the slope of the line. Here we have the velocity graph. So it's the biggest number at 0. It's at 2 or whatever this number is, right? So when does it go for the fastest backwards?
At 2.
At 2, right? So literally it's the bottom point here. And then when does it have 0 velocity?
1 and 4.
1 and 4, right? So that's slightly different from the position one. And now if we want to find the acceleration is the slope of the velocity graph. So when does it have positive slope?
2 to 4.
2 to 4. And then when does it have negative slope? 0 to 2, right? So looking at any one of these graphs, you can tell me about all 3 of the concepts: position, velocity, and or acceleration. Let's do a couple of these and then we'll move on to AP questions. A white ball is dropped from rest at the top of a building. At the same time, a black ball is thrown upward with initial speed of 30 meters per second. Use G equals 10 meters per second and let upward be positive. So we want to match the velocity versus time graph. So let's start with the white ball then. I'm going to use blue for the white ball. So a white ball is dropped, right? So dropped, what does dropped mean?
Free fall.
Free fall. And I didn't say this earlier, but that tells us that V naught is equal to 0, right? So that's usually free fall too. So we're starting at 0. And then we said free fall, right? So free fall also tells us that G is equal to -10. So then what does that tell us? Right, after 1 second, it's going to go down 10. 2 seconds, it's going to go down 10. 10, 10, 10. What about the black ball? The black ball, I'll use pink, you know, because black, pink.
Maybe you could draw a curve going downwards from 30 meters per second.
Where is it going to curve to?
When it curved down to I'm not sure.
Remember, free fall, so there's only one thing acting on it. It's only acceleration. Right, acceleration due to gravity. So if it starts at 30, what's gonna be its velocity after 1 second?
20 meters per second.
And then after another second?
10.
10, right? So you said the word curve, but I think the better word would have been line. Right? It's not gonna, I guess a line is a curve though, technically. So this would be the one of the black ball, right? There's no other things acting on it, just gravity, and gravity slows down velocity by 10 meters per second every second. Example, an object moves so that it has a v versus t graph as shown below. Change this representation into the object's acceleration versus time graph, then change it into the object's position versus time graph, assuming the object begins at x naught is equal to 2. Finally, draw a quantitative motion graph showing the object's position and arrows representing the velocity every 2 seconds. Okay, so what did we say? How do we get the acceleration based off of the velocity graph? What do we have to find? We want to find the slope of the velocity graph. So if we're finding the slope of the velocity graph, we're literally just going to count squares, right? So from here to here, it's up to, we have to, they try to trick us with the units, right? It's up to over 2. It looks like it's 1/2, but it's actually up to over 2. Right, so the acceleration from here all the way to here, right, all the way to here, it's the same acceleration, right? So from here to here, the acceleration should be 1. Yeah. And then now we're going to calculate the slope here. So now it's over 2 down 4, right? It's down 4 over 2. So the slope from here to here is -2 all the way to here, right? So slope is -2 all the way to here. And then what's the change of slope here? Well, there is no change in slope, right? So from 16 to 20, my velocity is just 0. Or acceleration, excuse me. My acceleration is 0. Does that make sense how I did that? The acceleration is the slope of the velocity graph. So then how do we go the other way then? They want us to find the position graph. How do we find the position graph based off of the velocity graph?
You find the area.
Let's find the area under the curve. And here we have to keep in mind positive and negative area. So if we want to do this one, the area from here to here is just going to be a big triangle, right? What are the dimensions of this triangle? Well, it's how much over? It's over 12. And then it's up how much? It's up 8, right? So from here to here, the position, we'll say x is equal to 1/2. Let me just do it from here to here, actually. I'm just going to do it from here to here, this part first. So this is 1/2 8 times 8. Right, so that's 32. So from here to here, I'm going to increase 32 units. Well, how much am I increasing? It says I'm starting from 2, right? X naught starts at 2. So if I start at 2 and I increase 32 units by 8 seconds, I'm going to need to end up where? I'm going to need to end up at about 34, right? 34, 34, 34, 34. So I'm going to need to end up here. And because my acceleration graph is positive, I'm going to curve concave up. So I'm not going to draw a straight line. I'm going to curve like this from there to there. Okay. Now let's look at the second part of this triangle, right? The second part of the triangle is how much it's from 8, 9, 10, 11, 12. So this is 4 units this way. This is 8 units up top. So x is equal to 1/2 4 times 8. So that's another 16 units. So from that point that I started at, now I'm going to go up another 16 units. So if I started at 32, I started at 34. 34 plus 16 is going to be 50. So by this point, I need to end up at 50. And since my acceleration is downward, I'm going to curve concave down to get to that point. Then this next part is another triangle. How big is this triangle? It's over 1, 2, 3, 4. It's 4 units across, but this one's down 8 units. So it's going to be 1/2 4 times 8. But now it's going to be negative 16. So I'm going to end up back where I started from. Then it's going to go back down to 34. It's a negative acceleration, so I'm going to curve downward again. And finally, this one's just a big old square, right? So then this one is going to be x is equal to 4 units by 8 units. So this square is 32, but it's beneath the x-axis, so it's negative 32. So that I end up back at 2. Since there is no acceleration, my graph is going to be linear from here to here. Questions about how the heck I did that?
My only question is telling when it's a negative. Is it just when it goes below the line?
When my graph is negative, that means I'm below the x-axis.
Okay, I see that.
Yeah. This is very confusing. So good thing I'm recording this. So if you need to like rewatch, you can rewatch. But basically, to go down from velocity to acceleration, we find the slope. To go up from velocity to position, we're going to find the area under the curve. Other questions? Okay. Oh, and then we need to do one of these things too, because we haven't done one of these yet, right? So it wants us to do a quantitative motion map showing the object's position and arrows representing velocity every 2 seconds. So every 2 seconds then. So if we start it here, what's the position every 2 seconds? So the position here would be roughly what, like 4-ish. So at 2 seconds, it'd be about here. And then we want to draw an arrow, right? And the arrow should be positive here. So that means we're going forward. Then why does it want every 2 seconds? Does it really want every 2 seconds? Okay, I'm just going to do a couple of them. So then at 4 seconds, where do I end up? I end up at positive 10, right? So this is at positive 10. Because I'm looking at this graph here, right? And then we're going to look at the velocity graph. At this time, now my arrow should be a little bit bigger because I have a higher velocity. So on the physics test, they want to make sure that you draw your arrows proportionate to each other. So this one should be a little bit shorter then. So this one should only be 2 units long. So notice I try to make it 2 units long to match up down here, right? So I try to make this one 4 units long. So then where do I end up at 6 seconds? At 6 seconds, I end up around 18, right? And 18, let's figure out what the velocity is at 6 seconds. So 6 seconds, 6 seconds, 6 seconds. Now it's 6 units long, right? So my velocity is 6 units long. So I want to make sure that I draw 1, 2, 3, 4, 5, 6 units long. Six seconds, where do I end up? I end up approximately at 18. So, oh, did I draw it at the wrong spot? Wait, this is 2, 4, 6. No, then I need to do 8. 8, 5, 6, 7, 8. At 8 units, I'm at 32, right? At 8 units, I'm at 32. Let's figure out what my velocity is at 8 units. It's at 8 meters per second also. I'm going to 1, 2, 3, 4, 5, 6, 7, 8 units long. then at some point, right, I'm going to have to draw negative arrows. Right, so I'll keep going this way and I'll da 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 da, and eventually I'm going to have to go like here and then go like this and here like this, right? Eventually, if I have to do negative arrows. Does that make sense what I'm doing or no? So I'm plotting the point where the position is, and then I'm taking that same velocity and drawing an arrow that's of a proportionate length to the velocity. Right, so I'm going to try to draw the arrow that many units wide. Usually they're only going to have you draw like 3 or 4 dots, not like 50 dots. That's a lot of dots for us to draw. Cool. Okay. So now let's look at some of these actual problems from the AP physics test. This should also be in your emails too, so if you want to have a printed version of this. So we have an elevator. It's on the 20th floor of a 40-floor building. And then at time t equals 0, the elevator is at rest and the doors have just finished closing. A student on the elevator has a smartphone with an app that can measure vertical acceleration. So you can call it an accelerometer if you want to use that. And the student takes data for the 10 seconds starting at t equals 0. The acceleration data is shown in the graph at the right, and let the positive values represent upward acceleration. So qualitatively and quantitatively describe the motion of the elevator at the following times. So at t is equal to 5 seconds, what the heck is this elevator doing?
Its velocity is constant.
That's true. That is true. Velocity is constant. What else can you tell me? Is it moving up, down, or not moving at all?
Wouldn't it just like not be moving at all?
What's your reasoning behind that, sir?
Well, if it's accelerating at like t equals like 2 to 4, then it's not accelerating anymore. It's probably just slowing. Wait. Actually, never mind. Wouldn't it? No. No, wouldn't it still be, wouldn't the velocity just still be positive?
The velocity would be positive, yes. So you caught yourself, right? Slowing down. Here, it'd be decelerating, right? But right now, it's been accelerating and then it stops accelerating, but that doesn't mean it changes the speed. So the velocity is positive. So if velocity is positive, that means it's going up, right? Can somebody help me figure out the exact value of the velocity? Or an approximate value of the velocity, maybe?
Is it 7.5?
How'd you get 7.5?
I found the area.
The area shouldn't be that complicated. 6?
Sorry, I tried to make a triangle. Forget it.
Oh yeah, no triangles here. This is a perfect rectangle, right? The dots are all similar. So we can say the velocity is positive. We can say positive 6 meters per second. Yeah, area under the curve. And I think that should be enough, right? Qualitatively, the velocity is constant. Qualitatively, it should be the elevator is moving upwards, right? Elevator moving up at constant speed. Or you can say constant velocity too here in this case, because here the speed and velocity. And then the quantitatively would be 6 meters per second. So now look at the second half. Now describe qualitatively and quantitatively at 10 seconds. Anybody have any thoughts?
Are we doing A2?
A2, yeah.
Oh, okay. The velocity is also constant at 10 seconds. And
Okay, velocity is constant, sure.
And it's negative 6 meters per second.
Interesting. So you have to remember that acceleration is the change in velocity, right? Acceleration represents the change in velocity over time. So if we did the area under the curve, this would be -6, right? But what is it changing -6 from? We found out at this point it was +6. So if it added 6, after the next bump, it subtracts 6. So the velocity is constant with a value of 0. Right, because we took 6 away from what we just added. Or if you want to think about it from the area thing, right, these two areas cancel each other out. So at time t equals 6, or t equals 10, excuse me, the elevator is not moving. So one of the hardest things I think about looking at the graph thing is you're like 6, okay, so that means that's the speed or something like that, but it isn't. It's the change. Every time you look at the area under the curve, it represents the amount of change. So at time t equals 10 seconds, is the elevator above or below or at its initial position? So now it's kind of asking for like some sort of position, right? So
Would
what
it
do you
be
think?
at the initial position?
Anybody else? Bronson says at. So to answer B, I'm actually going to go to C, right? They want us to graph the velocity graph over time. So let's do that, right? So from 1 to 2, it's not doing anything, right? It's not accelerating, and it said it starts at rest. So from 0 to 2, it's just like blah, just there, right? And then we found the speed or the velocity at 4 seconds, right? So it'd be 6 meters per second. So I'm just going to randomly call this 6 meters per second, +6. And so from here to here, it's going to go up, right? It's going to increase. And then from 4 to 6, it's not going to change, right? So it's going to be like bloop. And then from 6 to 8, it's going to drop back down, right? It's going to drop back down the same amount. And then from here to here, it's going to stay. Right? So this velocity graph corresponds to that acceleration graph. So if we think about it that way, how do we get from the velocity graph to the position graph? Remember that the area under the curve. So if we're to calculate this area, we don't need to calculate it exactly. But what is it? It's above the x-axis. That means the position that I'm going to accumulate is positive. It means the elevator is going to keep moving up. So what's happening with this elevator is it speeds up while it's going up, but then it starts to slow down. But it's slowing down while it's still moving upwards. So it never once changed direction. By looking at the acceleration graph, it looks like it changed direction, right? Oh, I went up, now I'm down, now I'm back at the beginning, right? So if anything, if you get a position question, it's like, it's not gonna be the obvious answer if you wanna think about it that way. So then we can do it with triangles here, right? So we're starting at y equals 0, right? So from 0 to 2, if you wanna graph this one, it would start at nothing, right? And then it's the area under the curve. So we can like do this triangle here. What is it? It's 2 by 6. So 1/2 2 by 6 is 6. So it's going to gather 6 units from here to here. Just randomly label 6 here. And then from 4 to 6, what is this triangle then? It's 2 by 6. So it's going to gather another 12. So it's going to gather another 12. So it's going to go up to 18. And then from 6 to 8, it's another 6, right? So it's going to gather another 6, so it goes to 24. And then it's going to stop. So maybe the graph looks something like this. So that's the visual representation of the position graph, right? It's going to increase and slow down. Questions on that? Okay, so this one's probably one of the hardest questions where you have to actually write complete sentences. Imagine having to write complete sentences on science. But they want to check your ability to do that. And then the other dumb part is that the students have like incorrect explanations. So you have to like correct their flawed logic. So it says 2 students obtain a yo-yo. One of them fully winds the yo-yo, fixes a free end to a hook, and releases the yo-yo so that it falls and it spins. The students observe that the yo-yo speed increases as the yo-yo falls. Each of the students state a hypothesis about the motion of the yo-yo as it unwinds and falls. Student A says, I think the yo-yo falls with constant acceleration. Student B is like, well, the yo-yo is falling, so the yo-yo is obviously exhibiting free fall motion. So in the space below, can you outline a procedure in which the students could follow in order to make the measurements necessary to experimentally test their 2 hypotheses? Explain how commonly available equipment will be used to make measurements. Draw and label a diagram of the experimental setup. So this one doesn't have like one right answer. So take a second and think through this and think. Anybody have thoughts on what kind of tools they want to use here?
Maybe a stopwatch and some kind of measuring stick.
Yeah, we can do measuring stick and a stopwatch. So then how would you calculate the, this one's hard though, then how would you measure it then, I guess is the question. Because what are we trying to calculate? We're trying to calculate acceleration, right? Because we want to calculate constant acceleration, right? So how do we calculate constant acceleration? We want to make sure that the velocity is increasing at constant rate. So if we want to figure out the velocity is increasing at constant rate, that means we want to figure out the velocity at different points in time. Because with the measuring stick and stopwatch, it's really hard to be like, okay, now boom, 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 boom. I mean, you could. And actually, according to the answers, you could say that and design an experiment. But does anybody know a device that will allow you to calculate a bunch of different speeds or a way of calculating it that way? Has anybody done one of these experiments with a bunch of things going really quickly? One of the things that you can use is you can use like a motion sensor. Right, a motion sensor will allow you to track the distance over the time. So like it'll take different dots and it'll graph it for you. So there's nothing wrong with the measuring stick and a stopwatch. It's just that the motion sensor gives you more data points. The other thing that you can do is you can, instead of using a stopwatch, is you can use a camera, right? Because with the camera, then you can freeze it frame by frame, right? You can calculate distance at different frames. Oh, at half a second, it's here. At another half a second, it's here. At another half a second, it's here, right? So you can actually literally compare the yo-yo next to the meter stick and see where it is in points of time. So video. And then in your description, you can say something along the lines of you want to like calculate the different points on the graph so you can calculate the change in velocity. That makes sense. And then you just like have a meter stick here, and then you're like, here's your camera right here maybe, and you draw the camera, and then here's the yo-yo, right? So here's the stick with the yo-yo, and it's like, okay, here, and then just like calculating where the yo-yo is on the meter stick. Out of curiosity, who do you think is more correct?
Student A.
Why do you think student A is more correct?
Because they're trying to measure the acceleration like as it's spinning at the end, correct? Rather than it dropping.
Mm-hmm. Anybody else? It's actually.
I thought
Go
student A would also be correct because the only thing I considered was the acceleration due to gravity.
Mm-hmm.
So that would, I guess, going with that, that would probably mean that it would be constant.
Interesting. So I kind of asked a trick question. I asked it in a leading way. I'm like, who do you think is more correct? They are both saying the same thing, actually. Because what did we say earlier? We said free fall motion, right? Free fall motion. What's the only thing acting on that force?
Gravity.
Gravity. And gravity does have constant acceleration. So they're literally both arguing, saying, oh, I think it's green. No, I think it's blue and yellow, right? Because green is just literally a mixture of blue and yellow. They're both saying the same thing. So I'm guessing that you're starting to notice that this test really isn't about computations. It's literally about understanding the words and the proper definitions of the words. So constant acceleration is technically free fall motion, and free fall motion is constant acceleration negative 9.81 meters per second squared. Yeah. So I'm gonna stop there because we're almost out of time, but I'm not going to give a bunch of homework in this class because you'll be doing practice tests, but there are like 2.5 more free response questions that I'd love for you to consider, and we'll go over them quickly next time before we go into the next lesson, because this is the nature of the types of questions you'll be seeing on the real test. Right? Anybody have any questions, comments, concerns? I'll also be uploading these documents into the Dropbox, and I'll share the Dropbox links with y'all. Cool. Alrighty, I will see you all later then.
Thank you.
All right,
Thank you.
bye-bye.